Hi guys, Mr. John here. In this video I want to talk about another modification that I did to the circuit. If you don't know what it is a boost converter based on dual sieve, which takes 3 volts from 2 AA's, boosts it up to 9 volts for any classic multimeter to use. So, I did make few videos about this circuit previously. I had 2 videos about this circuit to be exact. One video where I showed the circuit as you see it now, and another video where I talked about modifications that I did to decrease what to call it, like no load consumption basically. Something like this. Basically, when the multimeter this thing is connected to the batteries permanently, and when the multimeter was off, as is, this thing consumed something like a couple of 100 microamps. Alright. Then I did a modification, introduced a little bit of feedback, which you can see in another video. I'm gonna post links in description, so check those out before asking any questions. And that decreased no load consumption to 10 microamps. A great improvement. Here I'm gonna talk about the improvement that increases efficiency by over 10%, which is a lot. And that improvement may seem kind of bizarre, really. I don't know. The way I came up with that idea is just, I don't know how to explain this. It just struck me, and that's it. Basically what I did is I took this transistor, I broke its emitter off of the circuit's ground, and I whacked another transistor in series with from the emitter to the ground. So the circuit now looks something like, where the heck is that freaking paper? Alright, so the circuit now looks something like this. You can see the same kind of circuit. This FB means that it goes to the multimeter. I ain't gonna talk about this here because I already made a video talking about this. Again, check in description. Anyways, here you can see I added a MOSFET. Why MOSFET? Because I wanted to keep the quiescent current down as well, and I'll explain you why a little bit later. So here you can see an N-channel MOSFET, 2N7000 small signal MOSFET, gate of which is connected through a 6.8 kilo ohm resistor to the switching node. It does not make much sense really, but what this circuit does is whenever this transistor switches on, it will switch off this transistor, that will switch off this transistor, that will switch off this transistor. So there will be no more base current flowing from the supply into here. That may seem like a stupid decision which will kinda desaturate the transistor or something like that, but the output voltage stays where it should be while the input current drops. So let me show you that now. Here is the circuit slightly modified. This thing in the heat shrink is a 6.8K resistor. Here you can see 3 pins MOSFET. Here's that another transistor. You may just be able to see that this blob is not connected to this blob. This big blob is ground, this smaller blob is the emitter of the transistor I talked about. And there is a jumper on the other side which connects this over to here. You can see that wire right there. Now first what I'm gonna do is I'm gonna go and show you the consumption with the modifications, then I'm gonna go and put a little blob of solder across those two. By doing that I will bypass the MOSFET and connect the emitter of the transistor right to the ground as it was originally. Okay, the setup. You can see input current, output current, and output voltage. So you can see it's off right there. You can see there is something again off, on. It's in continuity mode right now. It's the biggest consumption. It's a range which consumes the most, about 7 milliamps. The output voltage is 9.26, 9.27 as you can see. Consumption is about average of 41 milliamps. Now I'm gonna blob over that thing. A blob has been placed right there. Okay, same stuff. Turn on, and tada! About 51 milliamps now. You can see it jumps around like, meh, it's about 50, 51. Does not matter all that much. You can see it. You can see a change here, and that means a lot. And the voltage, current, you can see is the same. Output voltage is 9.3. Not a whole lot of difference if you ask me. Now what that comes out as, let's just get this mirror out of the way so you don't accidentally see my mug. What the? Can I be organized in at least one video? So here are some numbers that I crunched previously. You can see original circuit, 9.3 volts output, 7 milliamps, 2.55 volts in the battery. The battery is holding up nicely. I did check it. This is a real voltage. I did not just go and transfer it here. It really was the same. Originally you can see about 51 milliamps input, 50% efficiency. Modified 9.27 volts, same current, same input voltage, about 10 milliamps less, which comes out at about 62% efficient now. An overall gain of 12%, which is a lot, and that is also consider that the output rectifier which I'm using is not a Schottky diode, it's just a regular old 1N4148. If you put a Schottky rectifier, you may gain another few percent of efficiency. So that's that. Thanks for watching, see ya.